In this video, we're going to showcase a proof of concept for creating a zero-touch CI/CD workflow in AWS. The end result will be a demo customer-facing Django app connected to an RDS Postgres instance behind an application load balancer in an EKS cluster. This app, along with all the supporting CI/CD add-ons, will automatically generate a subdomain with a working TLS certificate, use an external DNS to manage all the necessary CNAME records in Cloudflare. For continuous integration, a Jenkins pipeline configured with a GitHub webhook will detect the changes made to the main application and build and push images to ECR. In parallel, SonarQube will perform a static code analysis on each build from its own server. For continuous delivery, ArgoCD will pick up the new builds, apply necessary updates to the repository using Image Updater, and deploy the latest builds. Elasticsearch will gather all logs and make them accessible through the Kibana dashboard. Meanwhile, Prometheus will collect all the metrics and display them through the Grafana UI. All this will be triggered by Terraform, which will provision the infrastructure and bootstrap ArgoCD in 2 different stages to avoid any state management issues. In this demo, we'll be focusing on setting up the development environment and then showcasing the steps of the CI/CD pipeline. In our next videos, we'll explore the different automation techniques and outline the specific installation requirements for each application. To get started, we're first going to go to the repo and scroll down to the installation steps. Here, we're going to install all the required CLI tools using Homebrew. The tools are Git, GitHub CLI, Terraform, AWS CLI, Helm, and kubectl. Moving on to the GitHub configuration, this setup supports multiple Git accounts by automatically assigning SSH keys, eliminating the need for manual user switching. We're first going to take a look at our project structure. If you go to our projects folder here, we can see there's a few top-level directories like GitHub and GitLab. In this hierarchy, the top level corresponds to the service name, in this case GitHub, followed by the account name, and finally the repos. Let's go ahead and check that out on GitHub. Going to our main account, we can see the repos that have already been created. And in the second account, when we go to the profile, we can see that it's empty. This script is going to remove the global user from the .gitconfig file and link the SSH keys using the include if directives and additional .config files. Using this structure, there's no need to switch users, as we only need to clone the repos in the correct location. With that in place, we can go ahead and create the 2 key pairs in our .ssh folder and copy each public key in our GitHub accounts. We first generate the key for the main user in the terminal. Then, in our GitHub profile, go to our settings, SSH keys, create new SSH key, give it a name, and paste our public key and save. Now, let's go ahead and do that for the alternate account. And with that, our local development environment is set up for all of our source code management tasks. So let's keep scrolling down and configure the AWS CLI. Going to the AWS console here, we're going to click on Create User, give it a name, attach an admin policy, select that user, and create an actual access key. With those credentials in place, we're able to create resources in AWS. To authorize the GitHub CLI to create repos and webhooks, we select the alternate account public key, then copy the OTP and click on Authorize. Next up, we're going to create the actual repo we're going to push to. If you go back to our profile page and refresh, we can confirm that it's now present in the alternate account. Now we're going to create the webhooks. First, we edit the variable for our domain and GitHub user. Then we copy this command right here, which is going to use the GitHub CLI to create the webhooks using JSON. Going to our repo settings, we can verify the JSON output we got earlier through the dashboard. The next step is to clone the repo in our alternate user directory, then create our blank .tfvars file and open our IDE to fill in our API keys. For Cloudflare, we open the dashboard, and in our domain, scroll down and copy the zone ID. Then, for our API key, we're going to create a new token with custom settings following the required permissions shown in the README. Following that, we're going to generate a new classic token, give it a name, click on the repo permissions, then scroll down and generate the token. Next, we can go on to edit the env auto.tfvars file with our domain and repo URL. Then inside the Argo apps, ArgoCD, ApplicationSet, edit these two definitions with our repo URLs. Moving on, this command is going to set our remote repo URL, add any files that we've changed, commit and push our changes. If we refresh, we can confirm our repo now contains all our updated files. So next, we're going to provision our cluster using Terraform. Before we apply any changes, we need to first run the init command. This is going to set up the Terraform backend and download the required modules and providers. After that, we can run the apply command, which is going to first provision all the EKS cluster resources, deploy the core add-ons, and finally bootstrap ArgoCD, which is going to take over the rest of the deployment process. Although we're going to be verifying each of the stages by going to the UIs of all the apps, this will not be necessary at all for the complete workflow to run, as all the configuration is self-contained and does not need any user intervention from here on out. As soon as the Terraform apply command is completed, we can test the ArgoCD deployment by executing kubectl get pods in the ArgoCD namespace. Initially, we can use a kubectl port forward command to access the ArgoCD dashboard, while the CNAME records created by external DNS get propagated to our DNS server. After that, we can open the browser on localhost port 8080, use admin as username, and fetch the generated password from the Terraform output. The first CI/CD tool to load, besides ArgoCD itself, an image updater, is going to be SonarQube. It's deploying this order because SonarQube needs to be fully operational by the time the Jenkins pipeline starts. By this time, the CNAME propagation should be ready. So we can go ahead and log into argocd.yourdomain with the same credentials we use locally. Next, Jenkins will be deployed. We can go to the UI by browsing to jenkins.yourdomain and looking up the dynamically generated password in the parameter store. Once inside, we can see the pipeline that will already be running. This will start the SonarQube analysis, build the initial Django image, and push to ECR. When we access SonarQube in the same way we did before with Jenkins, we can see that it has created a project and completed the static code analysis. By this time, the Jenkins build should be ready. We can verify it's been completed by going to the ECR dashboard, which will have our artifact repo and a new image with a tag. Initially, Django's customization.yaml will have an image tag from previous deployments in our old repo. This will be replaced by the image updater when it sees the new build in ECR. ArgoCD will recognize when this change is made and finally deploy Django. Here we see Django, our demo customer-facing app. It's connected to an RDS Postgres instance, and it uses HTMX to dynamically update web content from the web server, functioning as a single-page application. By this point, the cluster observability apps will also be deployed. Let's start by checking out Elasticsearch via the Kibana UI. Logging in, we see that the Elasticsearch endpoint is created successfully. And we also see that the index, which is populated by Fluent Bid, has also been created. Using the dashboard, we can see the individual documents that are capturing all of the logs that contain information from the pods and the applications. Next, we're going to take a look at the Grafana dashboard, which contains the metrics aggregated by Prometheus. Here we can access the nodes dashboard, for example, which displays the CPU and memory usage of the pods in each node. To wrap up, we use the Terraform Destroy command, To prevent errors from resources created by ArgoCD outside Terraform's control, our setup includes a local exec provisioner. This automatically uninstalls ArgoCD apps and deletes the cluster resources before removing all the infrastructure, simplifying the teardown process without needing manual adjustments in the AWS console. Up until this point, we've gone over all the steps to set up our local environment and showcase a quick overview of the different CI/CD stages. In our next videos, we'll go deeper into different concepts that we've used to fully automate this workflow, including separating the infrastructure and application state files to prevent errors with resources created outside Terraform's control. Also using both Kustomize and Helm together to streamline the installation of third-party open-source tools. Leveraging external secrets operator to bridge the gap between infrastructure as code and GitOps and allow passwords and endpoints generated in the provisioning process to be defined in a declarative fashion. And other tools like ArgoCD CMP to use variables for elements that wouldn't normally be able to be defined dynamically, like AWS account numbers. If you've enjoyed this video, make sure to like and subscribe. Let me know in the comments for what topics you'd like to see covered in more detail in the future. Thanks for watching, and see you in the next one.